In this lecture, we will be discussing on the transitive closure of a relation. Suppose R is a relation on a set A, then we call the transitive closure of R another relation which we denote by R plus, such that R is transitive, R contains R plus is transitive, R is contained in R plus, and R plus is the smallest transitive relation containing R. So, there are 3 points to be remembered: R plus must be transitive, second point to remember is R is a subset of R plus, and the third point to remember is that if T is a transitive relation on A such that R is a subset of T, which in turn is a subset of R plus, then T equal to R plus. If for R plus the above 3 conditions hold, then R plus is said to be the transitive closure of R. Now, our problem here is to find out a way of computing R plus from R. We start by checking the powers of R, that is R composed by itself. So, we consider R and then we define R square, which is also written as R composition R, as A R square B if and only if there exists A 1 belonging to A such that A related to A 1 and A 1 related to B. In this way, we can extend the this idea to r raised to the power some k. So, we define r raised to the power k, which is essentially r composition and so on, r composition and composition r, and this whole thing is k times, all right, as a r raised to the power k b if and only if there exists a sequence of elements of A1 up to a k minus 1 all inside A such that A r A1, A1 r A2, so on up to a k minus 1 r A, here it is B. So, the last element here is a k minus 1 r B. All right. Now, the result that we are going to prove here is R plus, that is the transitive closure, R plus, that is the transitive closure of R, is same as R union R square union and so on up to R k, but we do not stop here, we keep on going. So, I just keep on taking powers of R and add in the union, and the totality that we get is R plus, that is what we claim here. So, I can in a compact notation write this is equal to k equal to 1 to infinity r raised to the power k. Now, the question is that where is the proof, and that is exactly that we are going to do now. We will write for the time being r prime as the union k equal to 1 to infinity r raised to the power k, and we will prove that r prime is indeed the transitive closure of R. So, to do that, first of all we have to prove that R prime is a transitive relation. 1. Suppose A R prime B and B R prime C for some A B C belonging to capital A. This means that there exists I comma j belonging to the set of positive integers such that A r raised to the power I b and b r raised to the power j c. This is because r prime is union of all r raised to the power k's, and therefore, if A is r prime b, then of course, there is some element I for which A is r raised to the power I b, and similarly for b and c. Now, by definition of the power of relations, what we have here is that there exists A 1 up to A I minus 1 and B 1 up to B j minus 1, all belonging to A, such that all right, we have a chain starting from A related to A 1 related to A 2, and we proceed in this way to A I minus 1 related to B. But what happens here, that the chain does not stop here, we can pick up from B, which is related to B 1 and B 1 related to B 2 and so on, and ultimately we come to B j minus 1 related to C. And therefore, if we combine this whole chain, then we will get A related to r raised to the power I plus j C. But this means that A union k equal to 1 to infinity r raised to the power k C, which in turn means that A r dash C. Thus, at least we have proved that r prime is transitive. The second point that we have to prove is somewhat easy, because we have to prove that R is a subset of R prime, and that is true because after all R prime is union of R and other powers of R. Therefore, it is easy to check that R is a subset of R prime. So, I will write here that it is easy to check. Next, we move on to prove probably the most difficult part of the proof, that is R prime is the smallest transitive relation containing R. We write it as the point 3. Now, let us think that how to prove this fact. So, I would like to prove that R prime is the smallest transitive relation containing R. That means, I have to prove that there is no relation containing R which is transitive and properly contained in R prime. So, let us suppose that we have a relation which let us denote by T, and which is sandwiched in between R and R prime. So, here suppose T is a transitive relation such that R is a subset of T, which in turn is a subset of R prime. What we will prove is that if such a thing happens, then T is forced to be equal to R prime, and that proves that there can be no proper subset of R prime which contains R and transitive at the same time. Now, to do this, we have to prove that T equal to R prime, and that means set theoretically T is a subset of R prime and R prime is also a subset of T. Now, this part of the chain already tells us that T is a subset of R prime. So, there is nothing to prove. So, we have to prove the other way around, that R prime is a subset of T. To do that, we have to start with an element of R prime. Now, suppose we have an element of R prime, we denote it by A B. Well, technically we can write A B belongs to R prime, which essentially means that A is R prime B, right, and this means, remembering that R prime is nothing but k starting from 1 to infinity R raised to the power k, all right. So, since A B belongs to R prime, therefore, A B has to be in some R raised to the power I for some positive I. So, therefore, I can write A R raised to the power I B, where I belongs to z to the power plus, that is positive integer, and since A is R to the power I B, we will have I minus 1 elements from A, such that we can build a chain of relations as we have seen before. So, this implies that there exists A 1, A 2, so on up to A I minus 1, all belonging to A, such that A are A 1, A 1 are A 2, we proceed like this, and then at end we have A I minus 1 R B. Now, in the next step we realize that by our assumption we have R a subset of T. Since R is a subset of T, all right. Since R is a subset of T, if we have two elements related through R, then they are also related to T. So, therefore, we can just change it to A T A 1, A 1 T A 2, and we proceed like this, and ultimately we will have A I minus 1 T B. Now, we know something more about T. We know that T is transitive. So, T is transitive. Why T is transitive? Because we have assumed it to be so. So, since T is transitive, what we realize is that we can kind of collapse this chain here to just A T B. Why? Because if you consider these 2 points in the chain, since T is transitive, we can write A T A 2, the next element will be A 2 T A 3, and if there is a next element to this, then it will be A 3 T A 4, and ultimately we will arrive at A I minus 1 T B. But then I can collapse it again, we can combine these two to write A T A 3 and proceed and ultimately get A I minus 1 T B. This is all because T is transitive, and therefore, at the end we will end up with A T B. But what does it mean? This means that the pair A comma B is an element of T, and therefore, we now check the whole chain of arguments. We started with assuming that the ordered pair A B belongs to R prime, and we end up by deriving that the ordered pair A B belongs to T. This means that R prime is a subset of T. Now, we check that we have already observed that T is a subset of R prime, and that is by the definition, and we have derived that R prime is a subset of T, all by using the property that T contains R, T is transitive and T is inside R prime. Therefore, we can write that T is equal to R prime, and this proves that R prime is the transitive closure of R. Now, as we have started by writing transitive closure of a relation by R to the power plus, therefore, we can write in symbols that R prime is equal to R to the power plus. So, that is to say again the same thing, that R prime is the transitive closure of R. Now, we will see that this whole thing becomes simpler if our underlying set is a finite set. We need to simplify this whole scenario, because as we have seen that if you give me a relation R, then R plus is a union of a infinite sequence of elements, namely R union R square union and so on, some maybe R to the power k and so on, which we are writing as union k from 1 to infinity r to the power k. Well, okay, theoretically we have proved this, but it is not necessarily true that we will be able to complete the computation in general, because we have to compute union of infinitely many elements. Therefore, we need something simpler, and we would like to have something simpler for at least finite cases, and indeed we have a much simpler result when the set A contains only n element, which we will write as A1, A2 up to An. Okay. So, by putting A within two vertical lines, we denote the number of elements of A, and in this case it is n. What we will show first is that suppose two elements in A, let us denote them by A and B, are related by some r to the power I of B, then we will, as we have seen before, have a chain of relations, so to say, connecting A to B. So, we will have elements like A1 up to A. I will rather change the notation over here, because I am writing the elements of A as A1, A2 and all these things. So, what I will be doing instead is that I will say that suppose there when we have got A r raised to the power I b, then we have some b1 dot 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 b I minus 1 belonging to A, such that A r b1 b1 r b2 up to b I minus 1 r b. Here we have to remember few things, that this b i's has nothing to do with the ordering a i's, and I may be much larger than n. So, and another thing that we have to note over here, that I have not told that b i's are distinct, they may repeat. So, I have essentially a sequence of elements b1, b2 up to b I minus 1, where there may be repetitions, and we may call it the sequence of internal points. Or the sequence of interior points. So, I will be calling them sequence of interior points. all right. Now, an element from the sequence, let us say B j, will be called interior point, and this whole chain starting from A and one after another a sequence of alternatively R and some B I, this whole chain is called a path from A to B, path from A to B in, we can call it in A with respect to the relation R. So, I can write it, I will just say it is a path from A to B if we assume that we know A and we know R. Now, there is an important parameter associated to this path, which is called the length of this path is simply I. Why I? Because we see that this 1, we have got 1, then 2 and like this. So, we will have I number of places where we are using the relation if we have I minus 1 interior points. Please note again that these interior points need not be distinct. If we think in terms of digraph, this is very intuitive. What we have here essentially a point A and a point B in A or in the set of vertices when we are looking at this whole setup as digraphs, then we have A and B and then we have some, let us say B 1 and a relation A related to B 1 means that we have a directed path. Then we again have something else B 2, then we have B 3, then we have let us say B 4, but this is where what I am coming to, that these interior points need not be distinct. So, from B 4 we may go back again to B 2, but then this B 2 is also B 5 and from B 5 we will go to B 6 and similarly we will proceed till we get to B from B I minus 1, and the number of links that we have used is essentially the length of the path. Now, what we will notice here, that if along the path a vertex or an element or a point of A is repeated, like in this portion B 2 to B 5, we can essentially cut this loop out and in the process reduce the length of the path. We can do this more systematically like here. Please see that I am first writing the path, this is A and this is A R B 1, then A R let me remove this, right, and then we have B1 R B2. Let us suppose we come to some B L minus 1 R B L, and then B L R B L plus 1. Again we proceed, then at some point we get another element, let us say call it B k minus 1 R B k, and then we have B k R B k plus 1, and we proceed again till we reach the end of the path, which is B I minus 1 R, and the last one is B. We have a path like this, and suppose B L is equal to B k, L is strictly less than k. Then as we have seen in the diagram, but in this case more formally, we can write a path from A to B as A starting from B 1 and so on till we reach B L minus 1 R, and here instead of B L I can just write B k. The reason is that B L and B k are same, and then continue in the same sequence to get B k, B k plus 1 and so on up to B I minus 1 R B, right. We get this. Now, of course, this is a path from A to B of length I. We have obtained another path from A to B of length strictly less than I, because L is strictly less than k, and well, what we have done is that we have cut out two equal interior points, just merged them and then gone on with our path. Now, we can keep on doing this process, and at the end we will have a path which does not have any repeated interior points. That means a path such that all interior points are distinct. So, continuing in this way, we can arrive at a path from A to B such that all interior points are distinct. Now, let us go back to the set on which we are considering the relation, this set has got only n elements a 1 up to a n, and so if we take any two points in A, if they are connected by a path, we know that we have already seen that we can, and we can always do that, connect A and B through a path where interior points are distinct, but these interior points are going to come from the set A itself and nowhere else. Therefore, if A and B are different and both are in A, the number of possible interior points that we can get is n minus 2. So, any path can be reduced to a path containing n minus 2 distinct elements of A if A and B are not equal. Therefore, the length of the path will be n minus 1. Suppose A and B are equal, then we are left with n minus 1 elements of A, and therefore, at most we can have a path with n minus 1 distinct interior points. In fact, it will be a loop starting from a point of A and going through the points of capital A and go back to the original point. So, the length of this path will be n. So, in this case, if we have two elements, if they are at all related by some r raised to the power I, they are related by some r raised to the power j, where j is strictly less than or equal to n and greater than or equal to 1. Therefore, r plus, which is union k equal to 1 to infinity r raised to the power k, is simply the union of a finite set of relations this. Now, we can do computation with this. Suppose we have to find out the matrix corresponding to the relation r plus, then it will be the matrix corresponding to the relation r union r square union and so on up to r raised to the power n, which in turn is the matrix M r or the matrix M r square and so on up to the matrix M r raised to the power n, which in turn is the matrix M r or the matrix M r square, the matrix M r raised to the power n, where this M r raised to the power I will mean M r and so on up to M r I times, where this particular operation is the operation of binary matrices that we have discussed before, which corresponds to the composition of the relations. This we have covered in previous lecture. So, we have this situation. Now, we can start checking an example. Yeah. So, let us take a set and a relation. So, now my set A is A, B, C, D and E, and the relation R is given by AA, AB, BC, CD, CE and DE. Our problem is to find R plus. In the first step, we construct MR. Now, if we check carefully, we will see that MR is 1 1 0 0 0 0 0 1 0 0 0 0 0 1 1 0 0 0 0 1, and the last row is all 0 like this. This we have to find out by finding the matrix corresponding to R that we have discussed in a previous lecture. Now, we keep on considering the powers of this relation, where M R square is nothing but M R multiplied by M R with the special rule that we have discussed before, and that will give us 1 1 1 0 0 0 0 0 1 1 0 0 0 0 1 and 0 0 0 0 0 along with 0 0 0 0 0. So, I will request you to check all the calculations, and I will tell you one way of doing this. When we are trying to compute M R square, which is M R product M R, what we can do is that we can just take matrix multiplication as such, and then at each entry we have to check that whether the entry is 0 or non-zero. If the entry is 0, keep it as 0. If the entry is non-zero, change it to 1, and then you will get a matrix like this. And if we try the same rule with M R cube, we will get 1 1 1 1 1 0 0 0 0 1 and rest of the rows all zeros, and in exactly the same way, multiplying M R 4 times by using the same product, we will get M R to the power 4, which is 1 1 1 1 1, and rest of the rows are zeros, all right. And then lastly, we have m r to the power 5, which is again same as m r to the power 4, all right. And then our job will be to take the union of all these relations, and in the matrix form it will be m r plus is equal to m r or m r square or m r cube or m r to the power 4 or m r to the power 5, and this, if we check carefully, is 1 1 1 1 1 0 0 1 1 1, then 0 0 0 1 1 0 0 0 0 1, and the last row is 0 0 up to 0, all zeros. So, this is the matrix corresponding to M r plus. Then we have to construct the relation corresponding to this matrix. For that, again we will use whatever we have studied before. We remember that in all these cases we have not tampered with the ordering of A. Therefore, these columns are labeled by A, B, C, D, E, and the rows are labeled by A, B, C, D, E. Therefore, we see that the entry corresponding to A gives 1. So, it is in the relation. So, A is in the relation, AB is also in the relation, AC is also in the relation, AD is in the relation, AE is in the relation. We come to the second row where we have B. We see that BA, the corresponding entry is 0. So, it is not in the relation, BB is not in relation, but BC is in the relation. So, we will write B comma C, then we write B comma D, we write B comma E. Then we come to the third row, CA is not in the relation, CB is not in the relation, CC is not in the relation, but it starts from CD. CD and CE are in the relation. So, we write CD, CE, and lastly we see that DE is in the relation and there is no other element in the relation. So, ultimately we have R plus as a set, and set, it is a subset of A Cartesian product A. Now, the problem with this technique is that we have to do lot of work, as we have seen that each time we have to keep on multiplying MR with whatever we have obtained before. What we are doing is probably little less complicated than matrix multiplication, but it is ultimately the same in terms of the number of elements that we have to compare in the worst possible case. Therefore, we would like to know whether we can do it in a faster way, and indeed there is an algorithm called Warshall's algorithm which does it in a much more faster and convenient way. This algorithm we will study in the next lecture. For today, this is the end. Thank you.